Welcome back, everybody. So you've got the COM 125 exam coming up. We've built this structured video lecture script based exclusively on your uploaded documents to help you study for your exam. We're cutting out the fluff and giving you a high-yield review on systems analysis and design. If you want to maximize that study time and walk into the exam room feeling totally confident, well, you are in the exact right place. Let's get into it.
Here's the game plan. We'll start with core system concepts, move into the systems development lifecycle, look at passing the feasibility test, explore analysis and design tools, and finally wrap things up with database fundamentals. We're building this chronologically from the absolute basics straight through to the databases that run the whole show.
All right, part one, core system concepts. What exactly are we building here?
Before we design a system, we gotta know what one actually is, right? This quote by Kenneth and Julie Kendall is exactly the kind of gold star academic definition your professor is going to look for on the test. A system is an organized collection of people, procedures, software, hardware, and data that work together to produce meaningful information. Notice that it's not just a random pile of tech. It is an interdependent collection working toward a very specific objective. Think about the human body or a university administration. If your heart suddenly stops communicating with your lungs, well, the whole system fails. Literally, the exact same rule applies to IT. Now, what's really cool is how that definition breaks down into the 5 C's, or components, you absolutely must memorize. You've got your physical devices, the hardware, the programs, which is the software, the raw facts and figures, or data, the users and IT specialists, so the people, and finally, the rules and policies, the procedures. It's like a giant puzzle. If literally any one of these 5 pieces is missing, the entire system just collapses. So, if you get a comparison question on the exam, you'll need to contrast manual and automated systems. Manual systems are operated by human effort, meaning they're slow and pretty prone to error. Automated systems require minimal human intervention, so they're incredibly fast and highly accurate. But here is the trap students always fall into: the cost. Remember this, manual systems are cheap to start, but they are super expensive to keep running because you're paying for human labor. Automated systems, massive initial cost, but they save the organization so much money in the long run. It's a classic trade-off. Similarly, make absolutely sure you can tell the difference between an open system and a closed system. Most real-world business systems, like a university, are open. They're highly interactive, they receive feedback from the environment, and they're highly adaptable. If they don't adapt, they die. A closed system is the exact opposite. Little to no interaction, zero external feedback, totally rigid. Think of a closed chemical reaction in a sealed lab. It just does its own thing, completely isolated.
Moving right along to section 2, the systems development lifecycle, the step-by-step blueprint.
Building a system doesn't just happen overnight. It follows a super strict framework called the Systems Development Lifecycle, or SDLC. This is your classic waterfall model, and you need to memorize these 7 sequential stages. 1, planning, which includes your feasibility study. 2, analysis, understanding what needs doing. 3, design, figuring out how it'll work. 4, development, the actual implementation and coding. 5, testing. 6, deployment, pushing it to users. And 7, maintenance. Burn this exact order into your brain for exam day. Okay, part 3, passing the feasibility test. Should we even build this thing? Before anyone starts drawing up blueprints, that very first planning stage requires a massive reality check. We call this a feasibility study, and it essentially asks, should we even proceed with this project? If this pops up on the test, anchor your answer to these 5 pillars. Technical. Do we have the tech in the brains? Economic. Do the benefits actually outweigh the costs? Operational. Will the users accept the system or will they completely rebel? Schedule. Can we finish it on time? And legal. Does it comply with data protection laws? Because trust me, nobody wants to design a system from a jail cell. If a project fails even one of these checks, management is probably going to pull the plug.
Section 4, Analysis and Design Tools, Blueprinting the Solution.
Once we pass feasibility, someone actually has to blueprint the thing. Enter the system analyst. Flashcard moment right here, memorize this definition. A system analyst is a professional responsible for studying existing systems, identifying problems, gathering user requirements, and recommending suitable information system solutions. They're basically the hero of the story, acting as the vital bridge between the end users who have a problem and the programmers who write the code. They need serious interpersonal skills just as much as technical chops. To communicate all those complex needs, the analyst relies on 4 specific visual tools:
A data flow diagram, or DFD, shows exactly how data moves through a system. A decision tree shows decisions and all possible outcomes. A decision table maps out conditions and actions in a structured grid. And a flowchart illustrates the system workflow and sequence. These tools eliminate all the guesswork, so the programmers know exactly what they're supposed to build.
When it finally comes time to design the actual interface, you have to follow 3 golden rules. 1. Place users in control. Ever used an app that wouldn't let you hit undo? Yeah, that violates rule number 1. 2. Reduce user memory load. Don't make people memorize random codes. Give them search functions and drop-down lists. And 3. Make the interface consistent. Keep your colors and button placements exactly the same across every single screen. And finally, Section 5, Database Fundamentals, the brains of the operation.
We can't talk about systems without looking at the back-end resource that actually stores everything. A database is an organized collection of related data stored electronically in a computer system for easy access, management, updating, and retrieval. Your professor will definitely be looking for this exact wording. It's the beating heart of most information systems, reducing data redundancy and letting multiple users grab what they need incredibly fast. Just like the SDLC, database design follows a strict, logical progression. You don't just dump data into a server. First, requirement analysis to figure out what data you even need. Second, conceptual design to map out relationships. Third, logical design to actually create the tables. And fourth, physical design, where you implement the whole thing using a database management system. Let's actually look at that logical design in action for a second. You see those vertical columns like student ID, name, and department? Those are called fields, and they represent specific attributes. Now look horizontally. Row 001 for John in computer science is a record. A record holds the complete set of information for one single entity. Actually, a good way to remember this for the test: columns are fields, rows are records. Super simple. You also need to know how these tables talk to each other. We have 3 main database relationships. One-to-one, which is like one student getting exactly one ID card. Then there's one-to-many, which is super common. Think of one academic department containing many enrolled students. And finally, many-to-many, where many students can register for many different courses. Nailing these relationships is literally what gives a relational database all of its power. All right, that is the whole shebang. We've mapped out the entire blueprint from the absolute basics through the SDLC past feasibility into the design tools and right down to the database records. Review these concepts and you are going to completely crush this COM 125 exam. But looking past the test for a second, remember that every single app, software, or network you use every day was once just an idea moving through this exact framework. So once you ace this exam, what system are you going to build to change the world?
Ever watched a massive project just totally crash and burn and found yourself thinking, man, how did they not see that coming? Well, if so, you are definitely in the right place. Today, we're decoding the absolute bedrock of system analysis and design. We are going to master the art and science of the feasibility study.
So, should we proceed with this project? It literally is the million-dollar question, right? It sounds incredibly simple, but getting this wrong is exactly how those massive, wildly expensive failures happen. Every business, IT pro, or entrepreneur has to ask this one single question before writing a line of code or signing a check. And our goal today is to show you exactly how to answer it with absolute confidence.
Okay, so what is a feasibility study? Basically, it's a preliminary investigation. It happens right at the beginning, literally, the very first critical phase of any system's development lifecycle. We use it to figure out if a proposed project or system is actually practical, achievable, and ultimately beneficial to an organization. It is the step that formally justifies the investment before anyone gets way too emotionally or financially attached to a doomed idea. Here's our roadmap for this explainer. We'll hit the ultimate go/no-go decision, the 5 pillars of feasibility, gathering the crucial facts, a real-world case study with ABC School, and finally, delivering the final verdict. Section 1, the ultimate go/no-go decision. It's all about mitigating risk and saving resources. A proper feasibility study prevents those catastrophic, costly failures by assessing viability way before you actually commit. You know how easy it is to fall into that sunk cost trap once a project starts, right? So the whole point here is to make sure time, money, and human effort aren't wasted on ideas that are just fundamentally flawed from day one. It helps leadership decide if a project should be confidently greenlit, strategically tweaked, or just completely scrapped.
Section 2, the 5 pillars of feasibility.
Any solid decision rests on these 5 pillars of inquiry. First up, technical. Is the tech actually available, and do we have the qualified personnel to pull it off? Say a school wants a crazy advanced e-learning platform. We have to ask, do they even have computers, reliable internet, the IT staff to keep it running? It's not just about buying shiny new servers, it's about evaluating that hidden technical debt. Can the legacy equipment actually handle the new system without completely crashing? Then we've got economic. Think of this as the ultimate financial stress test. We're asking, how much is this thing going to cost? And honestly, more importantly, will the organization actually gain from it? It's all about that ROI. If a system costs 1 million naira to launch, but saves 3 million naira a year in operations, will the benefits absolutely crush the costs? It's economically feasible.
Now, this one is wild. Operational. You can kind of think of this as the silent killer of IT projects. Because look, even the best, most cutting-edge tech will flat out fail if employees refuse to use it. We have to ask, will users accept the system? Are they going to adapt to a new workflow, like a fully automated payroll system? Operational buy-in from the people actually pressing the buttons every single day is absolutely crucial. If the culture rejects it, the whole project goes down.
Fourth is schedule, the time factor. Can the project meet the deadline, and are the resources there to finish it on time? Imagine building a totally flawless, brilliant grading system, but it gets delivered a week after term exams are already over. That system is effectively useless for that term. You've got to hit those hard deadlines.
And finally, legal. Simply put, this pillar ensures you don't get sued. It's all about compliance. Building a hospital database? Great, but does it strictly follow data protection laws for patient info? Do you have the right software licenses, or are you risking massive fines? You have to lock down company policies and industry-specific privacy rules, for sure.
Section 3. Gathering the crucial facts.
So we know the questions, but how do we actually get the data? Analysts use a few primary tools to extract facts from the current setup. We've got interviews for face-to-face deep dives, questionnaires to hit a large group quickly and cheaply, and observation, literally just watching users work to see what they actually do versus what they say they do. There's also document review for historical context, and then joint application development, or JADE. JADE is awesome because you lock all the key players, users, managers, analysts, in one highly structured room to hash out conflicts and get immediate unified feedback.
Section 4. Case Study. ABC School.
Okay, let's make this real. Right now, ABC School is stuck in a highly chaotic manual system. We're talking massive piles of paper attendance sheets, brutal manual fee tracking, lost student files, and stressed out teachers constantly making grading errors. It's incredibly slow. They want to propose a computerized, centralized school management system to fix data security and make finding information lightning fast. Let's run this through our pillars. Let's treat this like an investment pitch for economic feasibility. On the cost side, when you add up the tech, software, and training, you hit a one-time setup cost of 1.2 million naira. But look at the expected annual benefits: slashed paper costs, way better data management, huge productivity boosts. That totals 1.4 million naira in measurable value every single year. And boom, there's your aha moment, a net annual benefit of 200,000 naira. Because the 1.4 million in yearly benefits outpaces that initial 1.2 million cost in just the first year alone, this is undeniably economically feasible. It's a financially bulletproof move for the school. What about the schedule? The analyst mapped it out perfectly. Analysis and design wrap up in week 2, development takes us to week 6, testing and training are done by week 10, with final deployment in week 11. It's a crisp 11-week turnaround that fits right into the term. Schedule, totally feasible. Which brings us to Section 5, delivering the final verdict. So you take all those cleared checkboxes, technical, economic, operational, schedule, legal, and build the actual report. This is the anatomy of the final document. It kicks off with the problem statement, vividly showing the pain of the old system. Then it walks through the feasibility analysis, breaks down that cost-benefit and risk assessment, like maybe budgeting a backup generator for power failures, and finally hits them with the formal recommendation. For ABC School, the triumphant final verdict literally reads, "The expected benefits outweigh the costs, and the system will significantly improve administrative efficiency. The project is recommended for implementation. They conquered all 5 pillars with flying colors." So as we wrap up this explainer, think about the initiative sitting on your desk right now. What potential project could you save or courageously put a stop to by rigorously applying this framework and just asking, should we proceed today? A feasibility study isn't just bureaucratic red tape. It really is the ultimate tool for strategic confidence. Thanks for joining me, and keep exploring.